Hello, everyone. My name is Peter Boyd. I'm a PhD candidate in statistics at Oregon State University. And today for the Cascadia R Conference 2021, I'll be talking about the package that I developed called nphawkes within R. And it's sort of an introduction to nonparametric Hawkes process models. So as a quick outline, I'll first get into what exactly a Hawkes process is by providing a definition and some applications. And then I'll focus in on nonparametric methods. And finally, I'll then walk you through what the nphawkes package has to offer. All right, so a Hawkes process is also called a self-exciting point process. And this process is essentially just a collection of points in which one point or event can cause more points in nearby space and time. So we can think of this sort of as a two-part sequence in which we have background or parent events that happen randomly by some process, such as a Poisson process. These background events are then able to spawn or trigger child events. So we can think of a number of applications, most notably in seismology, where a main shock happens due to geological phenomenon, and that main shock can then trigger aftershocks. Now, we can also use these models to assess social networks such as Twitter. I might tweet something and one of my 4 Twitter followers can then retweet me and the process can continue. You're also, I'm sure, very well acquainted with the spread of epidemic diseases such as COVID, which can also be modeled in this manner where I may be COVID positive and can then spread it to a roommate and he can give it to someone else. So these processes are modeled via their conditional intensity function denoted lambda. And the conditional intensity is really just the rate at which we expect points to occur in some very small space-time window, given what we've already observed, the history of the process. So these self-exciting point processes were then further developed as epidemic type aftershock sequence models, or ETAS models. And the goal of these models is to estimate essentially two things: the background rate, again, that's just the rate at which these main shocks occur, and we denote that as mu. And we'll also then want to estimate how new events are triggered. So we can look at this model here as the conditional intensity again being lambda, which is a function of both space and time, and it depends on the history. And so this conditional intensity is then going to be equal to mu, or the rate, or the background rate, the number of events we expect to occur sort of naturally, plus however many triggered events we anticipate. So sort of as an example, let's consider that right now in Corvalis, Oregon, there is an earthquake that happens. And so we'll use this triggering function, or the functions g, h, and k, to assess how this event can spread. So g is a function of time, and it will then describe how likely we are to see this event that just occurred to trigger more events in maybe an hour or a day or a week. Similarly, h is a function of space, and it will then describe how likely this event is to trigger an additional aftershock, maybe in the nearby towns of Salem or Eugene or Portland. And finally, k is a bit different in that it's actually a multiplicative factor. And so if this event was a really large magnitude event, it's more likely to trigger a higher number of aftershocks. So these ETAS models were based on very well-studied seismological phenomenon in which they were able to define 7 parameters that sort of capture that triggering ability. Unfortunately, not all subfields have such a depth of research. Seismology has been studied for decades. So if we wanted to apply these ETAS models to new applications, we probably won't have that same knowledge of the real triggering ability of these events. So as a result, folks started using nonparametric approaches such as the model-independent stochastic declustering algorithm, which I'll call MISD. And it's an EM type approach that is based on what I'll call a network of pairwise triggering probabilities. And so we can think of these probabilities as what's the probability that some event I is responsible for triggering another event J. So this algorithm works by executing a few steps that begins with first calculating what the background rate is, which is, again, the rate at which those main shocks occur sort of naturally. After that, we'll then calculate those triggering functions, which govern how new events are spawned. And with those 2 bits of information, we'll then update those probabilities that one event triggered another one. And we'll repeat those steps a bunch of times, iterating until those probabilities stop wiggling around too much from one iteration to the next, and we say it's converged. All right, so that's sort of what self-exciting point processes are, as well as the MISD algorithm, the nonparametric self-exciting process. And so my goal here was to build a suite of functions that can be used to nonparametrically study point processes, self-exciting point processes. So this package nphawkes is a pretty easily implemented and fast package that was largely written in C++ along with R, using the Rcpp package to sort of fuse the two. And it's nice in that it requires fairly minimal inputs. You must use time, but things like space and magnitude can be included if the data has them available. So in order to get this going, we'll first want to run these lines of code as the package is currently available on GitHub. Now to walk through an example, I'm going to start by introducing the Hector Mine earthquake. Now this data set is included in the package, and the Hector Mine main shock was a very large earthquake that happened in October of 1999 down in the Mojave Desert of Southern California. And the data set includes 542 earthquakes over a 14-month span that follows that main shock. And this catalog or earthquake data set is used in several ETAS studies. Okay, so to actually implement this MISD algorithm within the nphawkes package, we're again going to use this Hector Mine earthquake data. And a lot of the MISD algorithm is based on these sort of bins that go into the triggering function. And so this triggering function is displayed as a step function and is plotted as a histogram, a probability weighted histogram estimator, which you'll see in a couple of slides here. And so in order to actually implement this algorithm, we'll have to define these bins over time, space, and marks. So we'll want to just ensure that we span the entire time, space, and magnitude domains. So we define these bins here, and then we'll use the MISD function to actually fit this model. And so we'll input the times at which they occurred, the locations in lat and lon, the magnitude, and then the data or the times of these events are all recorded as the time elapsed since the initial event. And so, or since the beginning of the catalog. So we'll specify these as being just in terms of times rather than in a time date format. And then we input our bins as defined above. And we'll also finally let our background rate be non-stationary such that it can vary over the entire spatial domain. Okay, so what did we find? Well, roughly 60% of the data were treated as background events. And this is an important thing to assess, as is typically the case with these self-exciting point process models. We don't know whether or not something was truly a background or a triggered event, or here a main shock or an aftershock. Additionally, we found that the Hector mine earthquake was responsible for triggering probabilistically around 97 aftershocks. And the background rate, again, can vary over space, but on average, we found about 0.9 main shocks to happen per day. And what was very nice was this algorithm took only about 11 seconds to complete. Okay, so here are these triggering plots that we found from this model. And so they can be very easily accessed by this trig plots function, in which we specify the model that we fit, and we'll include our standard error estimates here seen in these light gray boxes. And then just to make sure that we can focus on regions of interest, I've specified some X limits for the time and space plots here. And so what we're looking at is G, again, is for time, H for space, and K for magnitude. And what's nice about G and H in particular is that they're both actually densities. So we could interpret these as, if we integrate under this step function, we can find the probability of aftershocks being triggered within some temporal or spatial difference bin. So again, those bins that we defined on the previous slide are plotted here. So this is an example of one bin and another bin. So in addition to what I've talked about thus far, the package as well as the MISD function in particular is quite flexible. As I noted earlier, the data used here, the time recorded is the time elapsed since the beginning of the catalog, but we could have similarly, if the data allowed, we could have used the actual dates as well as the time of day for further specificity. And things like distance can be measured in something like miles or kilometers. And aside from what I've displayed here, we could also plot the conditional intensity over time, or plot the background rate over space as a heat map. And we can also perform a residual method called superthinning, which also we can visualize. All of these functions, along with some others, are available within the nphawkes package. So as some sort of final thoughts, this nphawkes package is especially useful for researchers who are just starting to get into nonparametric Hawkes processes. And it's, I think, a well-performing package in that it's pretty quick while requiring very few inputs that also can, of course, be very, very flexible. One bit of difficulty that might arise, the fit of the model does depend quite a bit on how we define those triggering function bins. Now, because the nature of a lot of these processes, most likely triggered events are more likely to happen in nearby space and time, which creates a greater need to model bins close to zero, or close to a time or space difference of zero. And so oftentimes these bins are defined on a log scale, which was done in this analysis. So that might be a useful thing to try out if you're throwing some of your own data into these models. And so in wrapping up, I have listed here a few references utilized in this talk that walk through some nice applications, as well as prove to be some very great sort of seminal pieces within this this area. So thank you for coming to my talk, and I hope you enjoy the rest of the our Cascadia 2021 conference.